Hi, today we're going to talk about how molecules are formed. So, before we really get into it, what we need to do is we need to think about, first of all, what a molecule is, and second of all, some basic principles that affect why molecules can form and what makes them stick together. So, first of all, a molecule is basically a collection of atoms, so maybe as few as two, possibly as many as hundreds of thousands if you're talking about a molecule like DNA, that are connected in a way that is very difficult to take apart. Molecules are held together by a very fundamental force that we call the electromagnetic force. So the electromagnetic force is a combination of electronic and magnetic factors. Most people understand this best in terms of magnets because that's what they played with when they were kids. But the principles are the same whether you're talking about electrical or magnetic, since they are governed by the same. So the first principle you have to understand, and I'm going to talk about this from the electrical point of view, but you can also think about this from a magnetic point of view, is that like charges repel. And the way you think about that from a magnetic point of view is if you have two magnetic poles that are the same, those would repel. So for example, you could have two positively charged things and they would repel or push away from each other. Or you could have two negatively charged things and those would also repel or push away from each other. By contrast, if you have charges that are different, or for magnets, poles that are different, different charges are going to attract. So they're going to pull towards each other. So in the case of electrical charges, that means you're going to have one positive charge and one negative charge. Another important thing to think about as we talk about electromagnetic forces is this equation that we call Coulombs Law. Now, I'm not actually going to have you calculate forces, but it's good to look at this equation and understand what it's telling us, because that helps us understand basic principles of how electrical charges interact with each other. So Coulomb's law, again, helps us predict the strength of an electromagnetic force. So this F here stands for force. This K thing is a constant. We're not going to worry about that because it never changes. And so, unless you're actually calculating, that doesn't really make much of a difference. These two things here are the magnitude of the charges. In other words, how strongly charged are they? So, for example, if you look at chemical ions, a lot of times you'll see like +1, +2, +3, or -1, -2, -3. Those are the magnitudes of the charges. And then finally, we have the distance squared. In other words, how far apart are the charged particles from each other? So let's look at the takeaways that we can get from this. First of all, the bigger your charges are, the bigger your electromagnetic force is going to be. And I should add, this is the magnitude of the charges. So +3 is a big charge, -3 is also a big charge compared to +1 or -1. By contrast, smaller charges will lead to smaller electromagnetic forces. And when I say smaller forces, I could be talking about smaller attractive forces or smaller repulsive forces. Both of those are valid. The bigger the distance between the two charged particles, the smaller the force will be between those particles, because we're dividing by the distance and squaring it. So then, of course, the smaller the distance between the two charged particles, i.e. the closer they are together, the larger the force between them. So that's something I want you to keep in mind. And now let's go on and talk about one more thing before we get into molecules, and that is basically the structure of an atom. This is really simplified. At the center of an atom, you have all of the positively or neutrally charged atomic particles, the protons and the neutrons, and those are all collected in one small area that we call the nucleus. And then there's a really huge area outside of the nucleus that is where the electrons hang out. Now, if you see the relative sizes, and by the way, this is not to scale, the nucleus is actually much smaller than that. You might think, oh, the electrons are huge, but that's not true. The electrons are actually really tiny. If we were to put the electrons to scale with the nucleus that I have there, you would not be able to see them because an electron is about 1,000th the size of a proton. So the electrons are tiny, they're in this area. The reason they take up that much area is not because they're huge, but because they are just moving all over the place. And so they use up all of the space, even though they're not in all of the space at the same time. So you have to understand that electrons are tiny. Yeah, they have a large negative charge relative to their size, but also they can move and they can be in different areas relative to the nucleus. So now let's get to molecules. Molecules, again, are two or more atoms stuck together. So one we talk about a lot in class is carbon dioxide. I often show it this way on my slides, where we have the carbon atom in the middle and the oxygen atoms stuck directly to the sides of the carbon atom. Sometimes you'll see it drawn this way, where you have the carbon in the middle, and then you have these lines in between the carbon and the oxygen atoms, and those lines are what we call bonds, which are the things that stick the atoms together. But what I want to do when I talk about how we form those bonds is I want to think about just two atoms sticking together. Because even if you have, a molecule of DNA that has hundreds of thousands of atoms in it, each of those are stuck together two atoms at a time. So atom A and atom B, and then atom B is not only bonded to atom A, but also to atom C, etc. So we can think of these as a whole bunch of two atom groups. So let's put in the two nuclei for those atoms. And the basic idea behind chemical bonding is that you have your two positively charged nuclei, and then you have an electron hanging out between them. And because different charges will attract each other, you have these electromagnetic forces that are pulling each of those nuclei towards the electron, and because they're both going towards the electron, they naturally move towards each other. Now, I want you to think about what would happen if you were small enough to interact with this system here, and so you grab the nucleus on, I think that's the left. It's always hard to tell because things are mirrored for me. And you pulled it away. If you let it go, because there is that attractive force pulling it back to the electron, it's going to go back to where it started. So that's the first thing you have to think about. Even if you have forces pulling it the other direction, there is always going to be that force pulling it back towards the electron. Okay, now let's think of the same setup, except what's different here from the last slide is our two nuclei are a lot farther apart from each other. So what does this mean for our electromagnetic force? Remember that according to Coulombs Law, we're dividing by the distance squared. And so, yeah, we're going to have electromagnetic forces, but they're going to be a lot smaller electromagnetic forces than we had in the previous slide. Now let's take that to the other extreme. Let's see what happens if we push those nuclei closer together, right? And you can see that if they're actually this close, yeah, they're going to be really strongly attracted to that electron because the distance is small, but also the nuclei are close to each other, and because they have similar charges, they're actually going to repel each other, and so there's going to be a strong electromagnetic force pushing them apart. So that doesn't work nearly as well as you think. Okay, let's think about another setup. Here we're going to put the electron kind of in between the two nuclei, but let's put it up here. Now you can see that, yeah, these nuclei are both going to be attracted to the electron. And if you think about it, if you actually get into like the vectors of it, which I'm not going to do too much in this class, but there is a component to that force that is pulling those two nuclei together. But there's also a component that's sort of pulling the nuclei up. And so only part of that force is actually holding the nuclei together as part of a chemical bond. All right, now I want to look at one last situation. So again, we have our nuclei in the same positions relative to each other, but now we're going to throw the electron in, we're going to throw it over here. So of course, for this nucleus right here, there's going to be electromagnetic force that's attracting it to the electron. And my question for you is, what about that? Is there an attractive force between this nucleus and the electron? Well, first of all, if there was, it would be a lot weaker than the other electromagnetic force that I drew in earlier, because the distance is much, much larger. So we have a possible really tiny electromagnetic force. But there's something else here, which is, look, there's this nucleus right here, which is positively charged. And we know that as this nucleus over here is pulled towards the electron, it's going to encounter a repulsive force from that other nucleus. And that ends up canceling out any sort of attractive force that it gets to the electron. So essentially, an electron in this setup does not at all help connect those two nuclei. Okay, so what does this mean for us overall? We can use electrons to hold the nuclei of atoms together, but that only happens when those electrons are in the correct places. That's the first takeaway. The second is there are optimum distances between two nuclei that you are bonding. If you have them too far apart, they're not going to stick together very well because of the great distance. But if you have them too close together, that's also problematic because then the nuclei will repel each other, right? So for every bond, depending on what sort of atom you have, there's going to be an optimal distance, and the nuclei will naturally settle into that optimum distance. So that is a very brief introduction. I hope this was helpful, and I look forward to applying this information in class. I'll see you soon.